This is the second part of chapter 2. In the first part, we discussed Laplace transform and block diagrams and transfer functions. At the end of that first part, we talked about the standard second order system, standard second order transfer function, and we mentioned that we are going to compare any second order transfer function with the standard one to find the values of zeta and omega n, and those are going to be used in the formulas that we will find later. This is where we're going to start finding those formulas. Time domain specifications. That is referring to specifications of a step response of a system. By step response, we mean the response of the system if the input is a unit step input. These specifications are at least five of these are very important to us. First one is delay time. We use TD to show that. Delay time. This is the time required for the response to reach half the final value for the first time, from 0 to half the final value. Next one is rise time. We use TR to show the rise time. This is the time needed for the response to reach the vicinity of its new set point, or basically the final value. The time it needs to go from 0 to its final value. Third one is settling time, TS. This is the time that the response needs to reach and stay within a range about the final value. That range could be different in different definitions. It could be 2%, it could be 5%, it could be 1%. We will talk about that with more details in a few minutes. Next one is overshoot. We use MP to show the overshoot. This is the maximum peak value of the response. This is only going to happen if we have an underdamped response, which has some oscillations and obviously an overshoot. If the response does not have any overshoot, any place where it goes above the final value, there is no overshoot. So basically overshoot would be 0. The last one is peak time, or TP. This is the time that the response actually reaches that maximum overshoot. So number 4 and number 5 are related. In the next slide, we will see these graphically on a sample step response. Here is how a step response of a second order system would look like. This solid black line is showing the response of the system as a function of time. And we can see all the specifications of the response discussed in the previous slide in here. For example, delay time, TD, as we said, it's the amount of time the response takes to go from 0 to half of its final value. The final value in here is assumed to be 1, which is the case in most situations. If the final value is, for example, 4, then half of that is 2, not 0.5. Pay attention to that. Next one is rise time, TR. One definition for rise time is when the time it takes for the response to go from 0 to its final value and reach its final value for the first time. This is when the response reaches the final value for the first time. It obviously goes over that, has some oscillations, it settles down at some different value, which could be exactly the same as the final value 1 or different. But what matters is that the rise time is the amount of time it takes for the response to reach that for the first time. Overshoot, you can see that here. This is the amount by which the response goes over its final value, and it's never going to go over that anymore. So the first time that it goes over, it's going to have the largest overshoot. After that, the undershoots and overshoots get smaller and smaller. So that's the maximum overshoot we're looking for, MP. This right here. The time that this happens is called TP, or the peak time, the time that that maximum overshoot happens. Last one is settling time here. Let's say we have an allowable tolerance of let's say 0.05 or 0.02, basically 5% or 2%. That determines this range around the final value. The time that the response goes inside that allowable region right here, and it never goes out of that region anymore, that time is called settling time. As you can see, this the response goes inside that region here for the first time, but that doesn't matter because it goes out of the region with that big overshoot and again comes back down inside the region, again goes out. But at this point, let me use a yellow color here. At this point, the response goes inside that allowable tolerance and it never goes out of that anymore. So that is our settling time. A couple of points about rise time and settling time. For rise time, we said the definition is the amount of time the response takes to go from 0 to the value of 1, for example. But sometimes the response does not actually reach the value of 1. That happens for an overdamped type of response where there's no overshoot. In those cases, one of these definitions could be more useful. The amount of time the response takes to go from 10% to 90% of its final value, or from 5% to 95%. With settling time, we always have to include that level of tolerance into our discussion. As you can see, with settling time, we have to say whether we're talking about a settling time with a 1% tolerance, or with a 2%, or with a 5%. These are the standard tolerance levels. The maximum overshoot is the last equation right here. The maximum overshoot percentage, in other words, written as percent overshoot. In short, sometimes we write PO for that. To find the percent overshoot, we find the amount of overshoot, which is the value of the response at its maximum, y at peak time, minus y at infinity, which is the final value, divided by y at infinity, which is the final value. That gives us the ratio by which the response goes over the final value. Just multiply that by 100, and that is the percent overshoot. So these are the definitions. After this, we're going to try and find formulas for each of these specifications of step response based on a standard second order transfer function. So let's first take a look at the first order system. A first order system with a transfer function like this. Consider this. If we want to find its step response, that means the input is the step input. The Laplace transform of a step input is 1 over s. So if we multiply the input by the transfer function, we have the output. So multiply input by transfer function, 1 over s by 1 over tau s plus 1. That would be our output. If we want to find the output in the time domain, or y of t, we have to do inverse Laplace transform. For that, we need the partial fraction expansions. So let's say the partial fraction expansion has been done. This is equivalent to 1 over s minus 1 over s plus 1 over tau. Tau here is a constant. If I apply the inverse Laplace transform on this, I can now find that the inverse Laplace transform of 1 over s is obviously the step function, the unit step function. The inverse Laplace transform of 1 over s plus 1 over tau is e to the power of negative 1 over tau times t. So 1 minus e to the negative t over tau is y of t. If I plot that, it's going to look like an exponential function that starts from 0 and goes up to the final value of 1. It never actually reaches 1, but it approaches a 1. As you can see, if you set t equal to 0 in the response we found here, you will find that e to the power of 0 is 1, so 1 minus 1 is 0. That's where we start. At very large values of t, we have e to the power of negative infinity, which is 0. 1 minus 0 is 1. So that's how it tends to the final value of 1. Based on the discussion on time constants from other courses, if you remember, after one time constant, the time constant here is tau, after one time constant, this amount of time, the response will reach 63% of its final value. After two time constants, 2 times tau, the response reaches 86%. These two are not very useful for us, but the useful ones are actually the next three. After 3 time constants, the response reaches 95% of its final value. At this time, it's going to enter the 5% tolerance level around its final value and stay there. So if our tolerance level for settling time is 5%, we can use 3 times the time constant to find the settling time. The next one, after 4 time constant, the response reaches approximately 98% of its final value. So after this time, the response will be within 2% of the final value. So if we want to find settling time with a 2% tolerance level, we can use 4 times the time constant. Last one, after 5 time constants, the response reaches 99% of its final value. So after this time, response will be within 1% of its final value. So for settling time with 1% tolerance level, we can use 5 times the time constant. The next slide, this was for the first order transfer function. Next, we'll talk about the second order transfer function and see where we can get that tau, the time constant. So we don't have the formula for settling time yet. Here's the second order, the standard second order transfer function. If I want to find the output of this system, when the input is a step, the unit step input, I'll do the same thing, multiply the transfer function by 1 over s, that is the Laplace transform of the unit step function. Then I will do the partial fraction expansions, which is this step going from here to here. And now we have 3 fractions there. If I do the inverse Laplace transform, at the end, after some manipulations, the response would look like this. I'm skipping the intermediate steps here because the response is what matters for us. There are some sinusoidal and sine and cosine functions inside that brackets that will create the ups and downs, the oscillations in the response. But what we are very interested in here is this piece, the exponential. E to the power of negative zeta omega n t. As you can see, zeta and omega n are the parameters of the second order transfer function. So they're coming from there. So if I want to write that e to the power of negative zeta omega n t as e to the negative t over tau, from there, by just comparing these two, I can find out that tau, the time constant, will actually be equal to 1 over zeta omega n. So keep that in mind. Tau is 1 over zeta omega n. So if I want to find settling time, I can use either 3 times this, or 4 times this, or 5 times this, depending on which tolerance level I want. Second order system response, we have already looked at this before. Another look at this, we can see that the response, the step response of a second order system could be like any of these responses that you can see here. This is how the response would look like. Time domain specifications depend on the parameters of the transfer function. There is an overshoot except if zeta is greater than 1. That is the overdamped type of response. And in most situations, actually, zeta will be somewhere between 0.4 and 0.8. The first one that we want to find a formula for The first step response specification is the rise time. We know that rise time, based on our initial definition, rise time was the time that the response reached its final value of 1. So in order to find the rise time, we can just take the formula we found for y of t in the previous slide and let t be equal to tr. So this would be the formula. I just replaced t by tr, and let that be equal to 1, because I want to find out for what value of tr this will be equal to 1. So I just need to set that equal to 1 and solve it. The ones on the two sides will be canceled out, and this will be true. This equation in the first row will be true if this second equation holds. This second equation is only valid if the tangent of omega d times r equals negative of square root of 1 minus zeta squared over zeta. So keep that in mind. Again, I'm going over the details or the intermediate steps quickly because we just want to get to the response, the answer. Let me erase this. So based on this, we can just divide both sides of the last equation we found by omega d, and we have our formula for rise time. 1 over omega d times inverse tangent of negative square root of 1 minus zeta squared over zeta. So keep in mind that when you want to use this formula, when you do the inverse tangent, that should be in radians and not degrees. This is a very kind of a difficult equation. So in most cases, instead of using this, we're going to use an approximate of this equation, which is much easier to use, and it's better for you to use this alternate equation. This sign in the middle must be an equal sign. So basically, TR, the rise time, is 1.8 over omega n. This is the first formula that we find for the time domain, the step response specification rise time, 1.8 over omega n. Remember that omega n is coming from the transfer function, the standard second order transfer function. Next, we want to find settling time. To find the settling time, we are first going to use this identity in the top to rewrite the function y of t that we found earlier that had a sine and a cosine inside brackets as this equation here. The reason we do this is because we need just a cosine to show up there, not both a sine and a cosine. And here we are also defining a new parameter beta, which is the inverse tangent of zeta over square root of 1 minus zeta squared. And to define our settling time, we don't even need that beta. Beta is only showing us what that equation of y of t is created from. What we care about is, as I mentioned earlier just before getting to the rise time, what matters here is that exponential term, e to the negative zeta omega n t. So there is a sinusoidal signal, something that goes up and down, but it's going to be confined within two exponential functions. I'm going to use a red color here, this exponential and this exponential. These are not the actual response. These are envelopes that are put around the response and are created by that exponential term. So because of that exponential term that's getting multiplied by the cosine, we know that the response is always going to be between those two red lines. So whenever those red lines go inside our tolerance level, inside between 1% or 2% or 5% of the final value, whenever those lines go inside, that means the response must also be inside, because the actual response would be somewhere between the two red lines. So that is why we can use the time constant of that exponential term, only that exponential term, to determine our settling time. As I said, the time constant from here, if we write e to the negative zeta omega n t as e to the negative t over tau, we can see that tau, the time constant, is 1 over zeta omega n. The tau itself is not the settling time, but either the 3 times tau, 4 times tau, or 5 times tau, depending on the tolerance level, will be our settling time. So going back to the graph that we had earlier with the settling, with the time constants, and reaching the 95%, 98%, or 99% of the final value, we get our 3 equations for the settling time. Settling time with 5% criterion, or 5% tolerance level, is 3 times tau, which is 3 times 1 over zeta omega n, or simply 3 over zeta omega n. The settling time with 2% criterion is 4 over zeta omega n. With 1%, it's 5 over zeta omega n. So be careful. Whenever you are asked to find a settling time, I'm sorry. Whenever you're asked to find the settling time, the tolerance level or the criteria for settling time must also be given to you. If it is not given, by default, you would be picking the 2% criterion. So if it's just saying find settling time and it's not saying anything, that means the tolerance level is assumed to be 2%, so you will be using the 4 over zeta omega n formula for settling time. So these are the formulas for settling time. Now we have formulas for rise time and settling time. Going forward to see the next ones. To find the peak time, that is the time that the response will have its maximum overshoot. To find this, we will simply use the equation we found for the response y of t and find its derivative, set the derivative equal to 0. Because when you find the derivative of a time function, set it equal to 0, the answers, the roots of that equation, are going to be the times where the maximums or the minimums of the function occur. The first maximum or minimum is our maximum overshoot we are looking for. So we take the derivative, we simplify the derivative. Again, I'm skipping the intermediate steps. And then we set that equal to 0 on the next slide. Set that equal to 0. That should give us TP, which is the peak time. This can be made equal to 0 only if this term is equal to 0. Because the term inside the bracket will never be equal to 0. It's not time dependent. Those are all constants. The exponential in the front will get close to 0 as TP increases, but it will never be equal to 0. So the only way this can be equal to 0 is if that sign is equal to 0. That sign of omega d TP will be 0 if omega d TP is either 0 or 180 degrees or 360 degrees, or the other angles equivalent to these. In radians, those will be 0 or pi or 2 pi or 3 pi and so forth. 0 will actually be corresponding to time 0. That's not what we're looking for. The first non-zero time where a peak occurs, or a maximum or minimum in the response occurs, is when omega d times Tp equals pi. So when omega d times Tp equals pi, then you can just divide both sides by omega d. That means Tp is pi over omega d. Very simple equation. This is our third equation, the equation for finding Tp. Omega d does not directly show up in these standard second order transfer function. The main parameters are zeta and omega n. But if you remember from previous part, the first lecture of on chapter 3, omega d can be found as a function of zeta and omega n. To find the maximum overshoot value, We know the maximum happens at time TP. So we can just use that TP we found in the previous slide back into our y of t equation, and that will give us the maximum value. If we just subtract 1 from the maximum value, because 1 is the final value, we will have the overshoot, the amount of overshoot. So we replace TP by pi over omega d, as you can see, here and here as well. Omega d times TP will be pi in these two places. Sine pi is equal to 0, cosine pi is 1, so the answer is simply this. This is the value of the output, y, at its peak time. As I said, we have to subtract 1 because 1 is the final value. We want to know how far the response goes above 1, so we subtract 1. And this will be the amount of overshoot, not the percent overshoot. The formula for the amount of overshoot, it's e to the power of negative zeta pi over square root of 1 minus zeta squared. If we want the percent overshoot, we should just multiply that by 100%. So this is the response, the formula for percent overshoot. Sometimes we refer to that as PO, percent overshoot. E to the power of negative zeta pi over square root of 1 minus zeta squared times 100%. This formula is valid when the final value of our response is 1, because as you remember, we subtracted 1 from the final value. So if we have a case where the final value is not 1, the equation will slightly change. But in most of our applications, the final value will be 1, and you can directly use this formula. Here's an example. This is a system given to us in the form of a block diagram. The block diagram has one block in the forward path. Its transfer function is given inside the block, and there is a feedback path, which is a unity feedback. It's a negative unity feedback. First step to solve the problem, any type of problem that has a block diagram like this, would be to find the closed loop transfer function. That is the transfer function from the input R to the output Y. Basically, we're looking for Y over R. To find this, we can use the techniques we learned to simplify block diagrams. If you remember, we had a technique to simplify a feedback loop. We said for a feedback loop, I'm going to draw that down here and then I will erase it. For a feedback loop like this, where the feed forward transfer function is G and the feedback is H, the feedback is negative. This feedback loop right here, the transfer function equivalent to that will be G over 1 plus GH. If we compare this to the block diagram we have in this example, we see that G must be this transfer function here, and H must be, looks like it's 0, but it's not, as we mentioned in the last lecture. H must be 1. Because the signal that's being picked up at this point on the output is being multiplied by 1 and then fed back to the beginning. So H is 1. So the transfer function should be basically G over 1 plus G, where G is that transfer function inside the block. So if that is clear, let's go ahead and erase this at the bottom. And now see the transfer function. The transfer function can be found as omega n squared over s squared plus 2 zeta omega ns plus omega n squared. If you're not sure about this, you can just write G over 1 plus G. G is omega n squared over s times s plus 2 zeta omega n over 1 plus the same thing, omega n squared over s times s plus 2 zeta omega n. If you do a common denominator at the bottom and then cancel the s times s plus 2 zeta omega n's from the top and the bottom, you're going to arrive at this transfer function. As you can see, this is exactly the standard second order transfer function we have been talking about before today in this lecture and in the previous lecture. In this example, the actual values for zeta and omega n are given. Zeta is 0.6, omega n is 5. What we want to do in this problem is to find the rise time, peak time, maximum overshoot, and settling time of the step response if this is our system with those values of zeta and omega n. You're going to see that it's very, very simple. We have a set of formulas. We'll just have to plug in the values of zeta and omega n and also omega d into the formulas, find the answers. That's it. Very, very simple. So we have the values of zeta and omega n. In one of the formulas, we need omega d as well. So let's go ahead and find that. This is the formula for omega d from last lecture. Omega n times the square root of 1 minus zeta squared. We plug in the values and find the answer to be equal to 4. Next, we just go ahead and write the formulas. It starts with rise time. Here's the original formula for rise time. As I said earlier, you have to be careful with that inverse tangent. It has to give you a positive answer, and you have to find that in radians, not degrees. Why positive? Because the rise time is obviously positive, not negative. If you plug in the values of zeta and omega d, this is what you get for rise time. Tangent inverse of negative 0.8 over 0.6. If you use a calculator and you find the answer in radians, it's going to give you a negative answer. Something like close to negative 1. If you ever get that using this equation, only in this equation, with that tangent inverse, you have to add pi to the answer, to that tangent, the answer of the tangent inverse. So for example, in this case, the answer of the tangent inverse given by the calculator is negative 0.927. You have to add pi to that. Don't forget that. Add pi and then multiply it by the 1 over 4 in the front. The answer comes out to be 0.554. So basically, we're expecting the response to reach the value of 1 for the first time at time 0.55. If you remember, we also had an alternate formula for the rise time that was 1.8 over omega n. You can also use that. This is a more approximate formula, so you should not be expecting to get an accurate answer using that, but it is okay to use that formula as well. For example, in this case, omega n is 5. 1.8 over 5 will give you 0.36. Obviously, that is different from what we found using the actual formula, the more accurate formula for the rise time. But it is okay to use that also. Next one is peak time. The formula for that is easier. That's pi over omega d. This is where we use omega d. We found omega d for this one. It was 4, so the peak time is pi over 4. The answer is 0.785. That means we're expecting the step response to reach its maximum value at time 0.785. The peak value, or the maximum value, is the value of the output at the peak time minus its final value, or basically 1 plus the e to the power of negative zeta pi over a square root of 1 minus zeta squared. This is the value of the output at its maximum, minus 1, which is the final value of the output. So the ones will cancel out. And this is telling us that the final value is 1. You don't have to worry about the case where final value is not 1. If you need to find out what is the final value, just to make sure, all you need to do is to use the final value theorem. You know y at infinity is going to be equal to the limit of s times y of s when s approaches 0. This is the final value theorem. We discussed it last time. This is the transfer function, if we want the output y of s, we just have to multiply that by r of s. So y of s is this transfer function times r of s. R of s, we are assuming that the input is a step, the unit step input. Its Laplace transform is 1 over s. So that's r of s, the 1 over s in r of s will get canceled by this s right here. So the limit is going to be the limit of omega n squared over s squared plus 2 zeta omega n s plus omega n squared. If you let s approach 0, these two terms are going to be 0. So the answer is omega n squared over omega n squared, which is 1. That's how you find out the final value of the output, that y at infinity is 1. Just to make sure we can use the person overshoot formula that we found earlier. Let me erase this so we can see the rest. So the maximum overshoot, the amount of maximum overshoot can be found based on the formula we had. Just plug in the value of zeta. This is the answer, 0.09. So that is the amount of overshoot. If you want that in percentage, just multiply that by 100%. So 0.0948 times 100 is 9.48%. This would be our percent overshoot. So basically, we're expecting our response to go over the value of 1 by about 10%, so almost reaching 1.1, and then it comes back down and gets closer to its final value. For settling time, nothing was said about the criteria or the tolerance level. So we can use, we should actually use the 2% criterion if nothing is said by default. So the 2% with 2% criterion, the formula is 4 over zeta omega n. Plug in the values of zeta and omega n. The answer is 1.33. This would be the settling time, the amount of time it takes for the response to reach and stay within 2% of its final value. If, for example, we wanted to find the settling time with 5% tolerance level, we would use the 3 over zeta omega n formula. It will give us a smaller value. Obviously, if you increase the tolerance level, the settling time will get smaller because it will take less time for the response to reach that larger tolerance level around the final value and stay within there. So let's check our answers by using MATLAB. Remember the formulas we found for the step response specifications for rise time, settling time, overshoot, and peak time. They are approximate formulas. You should not expect accurate answers from them, but they are acceptable if we have to do that by hand. If you have access to MATLAB, you can actually use your closed loop transfer function. Using the closed loop transfer function, create the array that has the numerator coefficients. Create the array that has the denominator coefficients. We already discussed this in another lecture. And then use the step command. That, if you run that, you're going to get the step response, something like this plot. This is something that you have to do in the first assignment too. So we want to find out what are those specifications of the response from the plot, and then compare those to our answer. For example, rise time, we found the answers that we found are written up here. These are the ones we found using the formulas in the previous slide. Rise time is the amount of time the response takes to reach the final value for the first time. So the rise time is here, the time that the response reaches 1 for the first time. As you can see, it's pretty close to the answer we found, 0.55. This one is a good approximation. The peak time was found to be 0.78. This is the time. This is when the peak happens, and this is the time that the peak happens. Close to 0.8, and our answer is also very close to 0.8. Good approximation. The percent overshoot was found to be 9.48%. If you look at this distance, the amount by which the response goes over its final value, its maximum overshoot, it's almost 0.1. So if you look at here, it's between 1 and 1.1, so the overshoot is about 0.1. So if you multiply that by 100%, you're going to get 10%. So our percent overshoot is also pretty good. Pretty good approximation of what it actually is. And settling time, our answer was 1.33 with the 2% criterion. The actual settling time, this is the time. This is when the response goes inside the 2% band, inside that region, and it never goes out of that after that time. If you check the time it happens, it's just before 1.2, whereas what we found was 1.33. So this is the one that has the largest approximation in there. But still, those are acceptable formulas for us. Most of the time give us a good approximation of the step response specifications. Also, remember that when you're using MATLAB, if you want to find the exact times that these happen, you can actually use the cursor, use the data cursor, and click on your response wherever you want, and it will give you the exact values, so that way you don't have to guess like what I did here, and you can get more accurate answers. Also, there is a command that you can use, step info. After you run the step command, you can run the step info, and then that will give you the settling time and rise time and everything else, all the specifications of the step response. But for the first assignment, don't use that. It is asking you to find the specifications first by hand and then using the plot, not by that step info command. Here's another example, a difference block diagram. This one is actually not given in terms exactly in the form of a second order, standard second order transfer function. So let's see what we have to do with this. The question is actually specify the gain of the proportional controller so that the output Y has an overshoot of no more than 10% in response to a unit step. You can just translate this to, we want the percent overshoot in response to a unit step function to be less than 10%. What is the range for K that allows us to do that? You see the proportional controller term here. This is our controller transfer function. And when you use a simple constant as your controller transfer function, that is called a proportional controller. It's just multiplying its input by a constant, so that's why we call it a proportional controller. More about this later. But here, let's just say we are using the proportional controller. That is the block diagram. We want to first find the closed loop transfer function, then compare that to the standard second order transfer function to find the value of zeta and omega n. Without zeta and omega n, we cannot use our formulas. So these are the first two steps. First, we need to find the closed loop transfer function. You should by now be able to do this quickly. As you can see, there are two blocks in series. Just multiply the two, and then there is a feedback loop. Just use the G over 1 plus GH formula. Remember that H, the feedback path here, is 1, so you're using G over 1 plus G basically. You simplify that, the answer is going to be this, K over S squared plus 2S plus K. As you can see, there's no zeta there, there's no omega n there anymore. So you have to write the standard second order transfer function right next to this, and then compare the two. If you remember, the standard second order transfer function was omega n squared over S squared plus 2 zeta omega n S plus omega n squared. Don't worry about the numerator at all. just look at the denominator. The coefficients of the denominator have to be the same. The coefficient of s squared here is 1. The coefficient of s squared is 1 here. If the coefficient of s squared in your transfer function is not 1, just divide the numerator and denominator by that number to get that equal to 1, because this is 1 here. Then compare the other two coefficients. Here, the coefficient of s is 2. The coefficient of s in the standard one is 2 zeta omega n. Set those two equal to each other. That gives you the first equation here. Then the constants, k must be equal to omega n squared. That gives you the second equation. That's all. This way you can find your zeta, you can find your omega n. If the value for k was given, you could actually find zeta and omega n as values. You could find the exact values for those, but here it would be in terms of k, obviously. So I'll erase this and then we'll see the rest. The person overshoot formula, we have the overshoot formula as e to the negative zeta pi over 1 square root of 1 minus zeta squared. We want the person overshoot to be less than 10%, so this must be less than 0.1. From here, we can find what should be the value of zeta to satisfy this inequality. To do this, you can find ln of both sides first. If you find ln of both sides, on the left, we're going to have negative zeta pi over square root of 1 minus zeta squared. On the right, you'll have ln of 0.1. Then multiply both sides by square root of 1 minus zeta squared. So this is canceled, and you have square root of 1 minus zeta squared multiplied there. Then square both sides, and then you will have zeta squared showing up on both sides of the inequality. Move both of the terms that have zeta squared to one side, everything else to the other side, and then at the end do the square root. Here's the final answer. Zeta comes out to be greater than or equal to 0.59. That means if zeta is greater than or equal to 0.59, then my person overshoot will be less than 10%. This is a key point. So now we go back to the zeta and omega n values that we found earlier, and then find out for what value of k this would be possible for zeta to be greater than 0.59. Erase this. Omega n is 1 over zeta, right? Based on this first equation here, zeta omega n is equal to 1, so omega n is 1 over zeta. If zeta is greater than 0.59, then 1 over zeta has to be less than 1 over 0.59. That means omega n has to be less than 1.689. If omega n has to be less than that, then we can just square that and find out what would be the maximum value for k, because k is omega n squared. So that's the final piece of the answer here. Let me erase this so we can see everything. K is omega n squared. If omega n has to be less than 1.689, omega n squared has to be less than 1.689 squared. So this gives the maximum value for k. So basically, k has to be between 0 and 2.853 for the overshoot to a unit step input to be less than 10%. So in this problem, we actually went the opposite direction. We started with a value for the overshoot, and we found one of the parameters of the system to have that specific value of the overshoot. So this could be also one problem that could show up in many places. So it's not always like you have all the parameter values and you want to find the specifications of the step response. This problem is actually more common. This is more close to a design problem. Your requirement is, for example, for the overshoot to be less than 10% based on your system, based on your application. And then this requirement, based on this requirement, you will find out what should be the values of your system parameters. One more thing to notice here is that if you don't feel comfortable working out this inequality, you can just change that equality to equality and actually find the value of zeta that will give you the 10% overshoot. That would be equal to 0.59. How do you know if zeta has to be greater than that value or less than that value so that we get less than 10% overshoot? Always have this as your guide. You remember the plot with all the different step responses with different zeta values. If you remember, for zetas greater than 1, you have 0 overshoot. So that should be your guide. That means the larger the value of zeta, the smaller the overshoot. So if you find out that for zeta being equal to 0.59, the overshoot is 10%, then you know for zeta being anything greater than 0.59, overshoot is less than 10%. If you use this, then you don't have to deal with this inequality when you want to find the value of that zeta. So taking a look at our step response for 3 different values of k for the same example. Let's say k value of 2, 2.8, and 3. Any value for that k will give me a different step response. It affects the system, it affects the transfer function, so obviously it affects the response. The blue line is the response when k is 2. The green one is when when k is 2.8, and the purple is when k is 3. Remember from previous slide, k has to be less than 2.8 something for the overshoot to be less than 10%. That red line over here is the 10% overshoot line. So we don't want the response to go over this. You can see that when k is 3, on the purple line goes above that 10% overshoot level, and that's what we expect. For the other 2 values of k, which are less than the value we found in the previous slide, the overshoot remains below 10%. So that confirms our answer. So the transfer function, the standard one that we were discussing so far, only had 2 poles, no zeros and 2 poles. The numerator was a degree 0 polynomial, denominator was a degree 2 polynomial. We found formulas for the specifications of the step response, but what happens if we have a transfer function which is slightly different? What happens if it has additional zeros or poles? We can still use those formulas to find the specifications of the response, but pay attention to the fact that the actual values might differ a little bit. And here we're going to briefly discuss what happens if we have additional zeros or poles. So first, if the transfer function is still a second order transfer function, but it has a 0, you can see the numerator is written as s over alpha zeta omega n plus 1. Denominator is pretty much the same thing we had before. It's just that the top and the bottom are divided by n omega n squared. So the 0 here would be set the numerator equal to 0, find the root, that will be negative alpha zeta omega n. That is the 0. If we said before that the location of the poles are negative sigma plus or minus j omega d, where sigma is zeta omega n. So if sigma is zeta omega n, now we know that the 0 is at negative alpha times sigma. So basically the 0 will be located alpha times away from the real part of the complex poles. That alpha plays an important role here. If alpha is large, the 0 is far away to the left of the complex poles, and it will have very little effect on the response. So we can actually neglect it. But if alpha is small, then the zero will be closer to the j omega axis. The closer the poles and zeros are to the j omega axis, the larger their effect will be. So if alpha is small, then the zero will actually affect the response. The plot on the right shows the step response for some different values of alpha, assuming a constant value for zeta. So let's say zeta is 0.5. For different values of alpha, you can see how the response looks like. If alpha is large, like 100, the response is pretty much what it used to be without a zero. So we could use the same formulas to find all the specifications of the response. If it's, say, 50, if alpha is 50, still we can use the same formulas. But you can see that if alpha is 4 or 2 or worse than that, 1, the response will actually change very much. The smaller the value of alpha, the bigger the overshoot we are going to see. The response will be faster. It reaches its value of 1 faster than before, which is a good thing, but the overshoot will also get larger, which is not so good. Step response of a second order system with a zero in the left half plane. If there is a zero in the left half plane, then we can write our transfer function as the combination of two transfer functions, and same way we can get the output of the system due to those two transfer functions. HO would be the transfer function like the standard second order transfer function. HD would be the part that has the zero in there. So you can see that the response due to HO is pretty much the same as the response we got for the standard second order transfer function. HD is not so normal. It goes up to 1, comes back down, goes even below 0, gets into the negative values, and then converges to 0. The total response will be the summation of those two responses, HO and HD. So we had the original response having no zeros, the response introduced by the zero, add them up, and that is the overall response. So you can see that the overall response will have a larger overshoot. The major effect of the zero in the left half plane is to increase the overshoot. So this is our result. It has very little influence on the settling time. If there is a zero in the right half plane, meaning that the zero is, for example, alpha times sigma, positive alpha times sigma, then HO will be the same thing, but HD, the response due to the zero, would actually start from the negative side. So if you look at HD, it starts from the negative side. It has an undershoot. That creates an undershoot in the total response. Overall response will start from 0, go into negative values, and then comes back up. So the summary is that the major effect of a zero in the right half plane is to slow down the response, and in many it may also cause an initial undershoot going below 0, going into negative values. So next we want to see what happens if we have an additional pole. So our standard second order transfer function had 2 poles. What if we have 3 poles? That additional pole, we can introduce that into the transfer function with that term in the denominator, get that factor in the denominator. If you set the denominator equal to 0, you will get 2 poles that are exactly like the 2 poles of the standard second order system from the term in the bracket. The other pole, the additional pole, will be equal to negative sigma zeta, negative alpha zeta omega n. That's the additional pole. Again, we introduced that alpha term to tell us how far away that additional pole is from the poles of the standard order system. Step response of several third order systems are shown here. So basically these are second order systems with an additional pole. Again, the value of alpha plays an important role. If alpha is large, then that additional pole does not do anything to the response. But if alpha gets smaller and smaller, and specifically if alpha is close to 1, then we have a big difference. So this is the case. This one is the case where the response is greatly affected by that additional pole. The major effect of an extra pole, as you can see, is to increase the rise time. It slows down the response, increases the rise time. If alpha is large, the extra pole has a little effect on the response. The pole and zero locations determine the character of the transient response. Basically changes those specifications: settling time, rise time, overshoot, and peak time. Here's a summary of the effects of those poles and zeros. A zero in the left half plane will increase the overshoot if the zero is within a factor of 4 of the real part of the complex pole. So basically, if that alpha is less than 4, the overshoot will be increased. If the zero is in the right half plane, it slows down the response and it may cause an initial undershoot. An additional pole in the left half plane will increase the rise time significantly if that alpha is less than 4. So if the pole is located within a factor of 4 of the real part of the complex poles, it will slow down the response, or in other words, it will increase the rise time. If the extra pole is more than a factor of 6 of the real part of the complex poles, further away from those complex poles by a factor more than 6, then the effect is negligible. We did not even consider the case where we have an additional pole in the right half plane. The reason is, if we have a pole in the right half plane, the response will actually be unstable. We discussed this before. Poles have to be in the left half plane for the system to be stable. So if that additional pole or any pole of the transfer function is on the right half plane, the response will be unstable. That means it will not be converging but diverging. The next topic is stability. Stability is very important. When we get to the design part, the first thing that we want to make sure our system satisfies is the stability. We want to make sure our system is stable, the response is stable, and then we will look at different characteristics of the response. This is the most important thing. So first let's see a definition of a stability. A linear time invariant system is said to be stable if all the roots of the transfer function denominator, which are poles, have negative real parts. Basically, we can say all the poles are in the left half plane. If that is satisfied, then our system would be stable. These are some of the examples of how the response will look like. If the real part of all the poles are negative, that means poles are in the left half plane, we'll have a stable response. So it converges to a fixed value. If there is a pole with a real value of 0, then the response will be oscillating and not converging to a fixed value. If the real part of the pole is positive, that means if there is a pole in the right half plane, the response will be diverging. It increases, so the system will be unstable. Again, the system is stable if its impulse response decays to 0 and is unstable if the impulse response diverges. This could be counted as another definition of a stability. But the condition is for all the poles to be in the left half plane. When we say poles, we mean poles of the closed loop transfer function. Pay attention to that. If you have a block diagram, you want to look at the stability, you have to first find the closed loop transfer function and then look at the poles of that transfer function. Stability of LTI systems. LTI, linear time invariant systems, are the systems we are considering in this course. They are the simplest type of systems, easier to work with. For these type of systems, we will go over some of the properties of stability and then find a technique to analyze the stability of the system. We have a closed loop transfer function. We need to set the denominator of that transfer function equal to 0 and solve it to find the poles. We said the poles will determine whether the system is stable or not. So that the denominator of the closed loop transfer function is very important. That's why we're going to give it a name. We call that, when we set that equal to 0, we will call that the characteristic equation. So let's say our characteristic equation is an nth order equation in this form. Assume that the roots, which would be the poles, are distinct, be either real or complex, but distinct. That means they're all different. We don't have repeated poles. In that case, we can rewrite our transfer function in this form at the bottom. This symbol means the multiplication. So basically the denominator here is equivalent to s minus p1 times s minus p2 times s minus p3 and so forth. So if we have n poles, we have n of those factors getting multiplied in the denominator. The numerator will be similar, except that instead of poles, we will have zeros, zi's, showing up in the numerator. But what matters here is the denominator, s minus p1 multiplied by s minus p2 multiplied by all those other similar factors in the denominator. If you set that equal to 0, obviously you will find p1, p2, p3, and so forth as the poles of the transfer function. The solution of the system response found using partial fraction expansion may be written as the summation of ki times e to the power of pit. The reason is, if we go back to the transfer function in the previous slide, with all those s minus pi's in the denominator, if we apply the partial fraction expansion on it, we will have fractions with s minus pi's in their denominators. A constant ki over s minus pi is the Laplace transform of ki times e to the power of pit. So the inverse Laplace transform of the summation of all those fractions will be the summation of ki times e to the power of pit. Why is this important? Because if we need to look at that e to the power of pit. If all the pi's are negative or have negative real parts, if we want to be more accurate, then all those exponential terms will converge to 0. And that means the response will be converging to a constant value and not diverging. If there is even one of those pi's that has a positive real part, then the response will be increasing with time. As t increases, that exponential term will increase, and the response obviously will be unstable. That also confirms the fact that we want all the poles of the transfer function to be in the left half plane, having negative real parts for the system to be stable. So as we said, this situation happens if all the poles of the system are strictly in the left half plane. In other words, real part of all the poles are negative. If any left half pole is repeated, the response will change because a polynomial in T must be included in place of Ki. So we will have terms like this showing up in the response if there are repeated poles. What matters here is that, again, we have that exponential term. And that exponential term will go to 0 if a is positive. Here we are assuming that the pole is at negative a. So the stability of a system can be determined by computing the location of the roots of characteristic equation. These are the poles. And determining whether they are in the left half plane or not. If they're all in the left half plane, we say the system is stable or internally stable. If a system has any poles in the right half plane, it is unstable. If a system has non-repeated poles on the j omega axis, that means poles that have zero real parts, the system will be called neutrally stable. If the system has repeated poles on the j omega axis, however, the response will be unstable because terms like this will show up in the response. And as t increases, as time increases, these terms will not decay. This can be shown by using Taylor series expansion of that exponential term. We don't have to go over this, so I'm going to skip this slide with some of the details. What's important for us is to understand that the poles have to be all in the left half plane for the system to be stable. Routh's stability criterion. This is a tool that we can use to simplify stability analysis, especially if we want to just do it by hand and we don't have tools like MATLAB to do the work for us. So let's say we have a characteristic equation in this form. We want to find out what is Routh's stability criterion, how we can use that, and then see some examples. So the characteristic equation, that is the denominator of our closed loop transfer function, is given like that. We have some coefficients. We normally would like the coefficients of the highest power of s to be equal to 1. If it's not 1, you can easily divide the top and the bottom of your transfer function by that value, and then you will have the coefficient of s to the power of n, the highest power of s, equal to 1. If that's equal to 1, then there are lower powers of s which have other coefficients, let's say a1 through an. These are constants. And in real examples and problems, those will be numbers. Routh's stability criterion allows us to analyze the stability of the system without actually solving the characteristic equation. So one way to analyze the stability, as we discussed so far, is to just set that equal to 0, find the roots, and then find out if all those roots have negative real parts. That is the first way. But especially in the cases that we have a higher order of a characteristic polynomial or characteristic equation, something of an order of 4 or 5, or 6 or higher, then finding the roots are difficult, especially if we want to do it by hand. Again, if we have tools like a calculator or a MATLAB to solve that equation for us, there is no need for a Routh's stability criterion. But at the time this method was created, those tools did not exist. And still, it's a good method to learn and be able to use. Sometimes you don't have those tools. And especially it will also give us some better understanding of stability. So here is the first notes about Routh's stability criterion. A necessary condition for stability of the system is that all the roots of its characteristic equation should have negative real parts. A necessary condition for stability is that all coefficients of the characteristic polynomial be positive. Remember, this is only a necessary condition. But it is good to always check this necessary condition, because if you have a characteristic polynomial, the denominator of your transfer function, such that some of the coefficients are negative, some are positive, then you know this necessary condition is not satisfied, so you know for sure that the system is not stable. But if you have a polynomial in the denominator of a transfer function where all the coefficients are positive or all of them are negative, that works also if they're all negative, then you have the necessary condition satisfied. However, you won't know if the system is stable for sure or not. So you have to do the rest of the process. But always check this necessary condition first. This is also equivalent to saying that if a system is stable, then all the coefficients of the characteristic polynomial are positive. Another way to write that necessary condition. Once the elementary necessary condition is satisfied, then we can use the Routh's stability criterion, which was created more than 100 years ago. A system is stable if and only if all the elements in the first column of the Routh array are positive. We still don't know what the Routh array is or how to set it up, but here's the condition. It doesn't look so difficult. It's very simple. If we have the array with some numbers in it, we just have to check the first column, make sure that all the numbers in the first column have the same sign, or they're all positive. If they're all positive, then that means the system is definitely stable. So this is how we're going to check the stability using the Routh criterion. This is also identical to saying the system is stable. If a system is stable, then all the elements in the first column of the Routh array are positive and vice versa. Another way of writing that if and only if condition. But how to get that Routh array? It's a pretty straightforward procedure. We're going to start with our general form of our characteristic equation. We first arrange the coefficients of the characteristic polynomial in two rows. We are going to label the rows with s to the power of n as the first row, s to the power of n minus 1 as the second row, and we continue this until we get to s to the power of 0. So we actually will have n plus 1 rows in the Routh array. The first two rows will be completed very easily. We just take the coefficients of the characteristic polynomial and place them into the first two rows with the order that we're going to see here. I'm going to label the coefficients that we see in the characteristic polynomial here. The coefficient of s to the n is 1. I'm going to label that with a 1. The coefficient of the next coefficient is a1. Let's label that with a 2. Then 3, 4, and so forth. So what we're going to do is to put the first one here in the first row, first column, first row, second one in the second row, but first column. Then we go back to the first row, put the third one there. We go to the second row again, put the fourth one here, and then go back to the first row, put the fifth one here, and we're going to continue this until we put all the coefficients into the first two rows. So we put one in the first row, then in the second row, back to the first row, then second row, and continue this. So setting up the first two rows are very easy. So now we know how to set up the first two rows of the Routh array. We have already put all these 1, A1, A2, A3, A4, A5, and the rest into the first two rows. How to get the values in the next rows? Start with the third row, which is actually labeled by s to the n minus 2. The terms in that row, I just called them B1, B2, B3. So we need to find these three. We will find that all the values in that row, and then move on to the next row. I'll find all the values in that row and continue this until we get to the last row in the array. So let's see the formulas. The formulas for B1, B2, B3. These are formulas based on the two rows above. B1 is A1 times A2 minus A3 divided by A1. B2 is A1 times A4 minus A5 over A1. Similarly for B3 and other values, all other terms in that row. Take a look at the next row, C's. If we want to find C's, you can see the formulas for C1, for C2, for C3. They all have the terms from the two rows above that row. So basically the terms from this row and from this row. For example, C1 is B1 times A3 minus B2 times A1 divided by B1. You can use these formulas, or you can use a general formula for term I in each of the rows. And I personally prefer that. I'm going to write that formula here. It's not included in the slide, so I will write that here, then I will erase it, and we will see the rest of the slides. If you like that, you can use that formula, which will basically be an easy formula that will tell you how to find each of the terms, each of the unknown terms in the root array. If you look at the B1, B2, B3. You see in the denominator, they all have A1. That's the first term in the row above. If you look at the formulas for C1, C2, C3, you see they all have B1 in their denominators. That's the first term in the row above of the C's. So we already know what's in the denominator. The numerators look like a determinant. So let me write the formula here. So term I in each row equals. In the denominator, we have first term in the row above. That's easy to find. In the numerator, we have negative of a determinant. In that determinant, we have two columns. That's a 2 by 2 determinant. The first column is first column from the two rows above. The next column, I'm going to use a different color for that. The next column is the column I plus 1 in the two rows above. Let's check that with, for example, C1. If I want to find C1 using this formula, this general formula, C1 is term 1 in that row. So to find that, we already know what shows up in the denominator of the formula. In the denominator, we'll have the first term in the row above, which is B1. So that checks. In the numerator, I'll have negative of the determinant of the first column in the two rows above, and the column I plus 1. I is 1. We are looking at the first term in that row, so I plus 1 would be this column. So determinant of these four put together, but don't forget the negative sign in the front. The determinant would be A1 times B2 minus A3 times B1. Negative of that is B1 A3 minus A1 B2. That is exactly what we have here. If you want to check that for C2, you will see the same thing. For example, to find C2, to find the second term in that row, the determinant in the numerator would be the determinant created by the first column in the two rows above, and the column I plus 1. I now is 2, so I plus 1 will be 3. Basically the next column, the column after 1 to the right of the term you want to find. So the determinant would be A1 times B3 minus B1 times A5. Negative sign in the front changes that to B1 times A5 minus A1 B3. That is exactly what we have here. So using this formula, you can get the same, you can get all those formulas for finding B1, B2, B3, C1, C2, C3, and all the other terms in the next rows as well. If this looks comfortable to you, use this one as a general rule for yourself to find all the terms in the root array. Now I'm going to erase this so we can see the rest. After we complete the table, we only need to look at the first column. However, it's not possible to look at the first column, just find the values of the first column, because the terms in the next rows will depend on all the terms in the rows above. So we have to complete the entire table to be able to look at all the terms in the first column. After we complete the table, look at all the terms in the first column. If they all have the same sign, that means all the poles are in the left half plane, means the system is stable. If there is even one term that has an opposite sign, one negative term and the rest are positive, that means the system is unstable. If the elements are not positive, then the number of roots in the right half plane equals the number of sign changes in the column. So that means if we start from the top and we have two positive numbers and then a negative one and then another positive one, that means from the top to bottom we will see two sign changes. That means there are two poles on the right half plane. As we said earlier, if there is only one sign change, that means the system is unstable. That's it. It doesn't matter whether there's one sign change or 100 sign changes in the first column. It's unstable. But still, this is some additional information that the table can give us. If there are n sign changes in the first column from the top to the bottom, that means there are n poles on the right half plane. Let's see an example. We have a characteristic equation. Normally, we should actually start with a transfer function or a block diagram. If you start with a block diagram, first find the closed loop transfer function. Then look at its denominator. Its denominator is going to be your characteristic polynomial. In this example, we skip that part. The polynomial is already given to you. So what we want to do is to check the stability by looking at that polynomial. We don't want to set that equal to 0 and find the roots. So let's instead use the roots array. Look at the coefficients in the polynomial. They're all positive. That means the necessary condition is satisfied. This should be always the first thing you will check. If there is only one that is not positive, and that means the system is unstable, you don't have to do the rest. This is a shortcut. But in this case, we see they're all positive, so that means it could be stable or it could be unstable. It means we have to do the rest. Now we determine whether the roots are in the left half plane or not. We start by labeling all the rows, s to the 6, s to the 5, all the way to s to the 0. First two rows are easy. We just take the coefficients from the polynomial, put in the first row, second row, first row, second row, and so on. The coefficients you can see from the polynomial, we have 1, 4, 3, 2, 1, 4, 4. We just put those in the table. And pay attention that your polynomial should be exactly in the same order. So you have to start with the highest order of s and get to the lowest order of s, or actually the constant at the end. It should be exactly in the same order. And also pay attention that if you have, for example, a 2s to the power of 4 plus a 3s to the power of 4 in your characteristic polynomial, you have to combine these two. So combine them into a 5s to the power of 4. And then your 5 will go into the table, into the first two rows. Don't put both the 2 and the 3 in there. So pay attention to this. Your characteristic polynomial should first be written in the exact same form. Then you put the coefficients into the first two rows. Then we need to find the coefficients into the next rows. The one here, for example, would be using our formula, it would be equal to the negative of the determinant, first column in the two rows above, so 1 and 4, then the next column in the two rows above, 3 and 2, divided by the first term in the row above, which is 4. So this is, determinant is 2 minus 12, that's negative 10. Negative of that is positive 10, so this is 10 over 4. If, for example, we want to find this one, this term, we will write negative of the determinant of the first column in the two rows above, 1 and 4, that doesn't change. The next column, the column after the term we want to find in the two rows above, are again 1 and 4. The denominator is still the first term in the row above, that is 4. That determinant is 0, 4 minus 4, so the answer is 0. Same way we can find all the terms in that row. Let me now erase these and see the answers. So we find B1 as we discussed. We found 10 over 4, that's the same as 2.5. B2, we found 0, you see it's 0. And then the next one, that is 4. We go to the next row, we do the same thing with the next row. We find C1 and C2, they are 2 and negative 2.4. We go to the next row, we find D1 and D2, we get 3 and 4. Go to the next row and find everything else. As you can see, for example, in this row right here, we only find the first two elements. We don't find the third element. The reason is if I want to find the element here, when I write the formula for that, I have negative of the determinant, first column in the two rows above, that's here, 4 and 2.5. Then the column after the term I want to find in the two rows above, here. Whenever you don't see anything in the table, that means it's a 0. So that is a 0 and a 0. That determinant is 0, regardless of what we have in the denominator. So we have a 0, that means we don't have to continue that row. So that gives you a rule. That means if whatever term that you want to find in a row, you have zeros in the two rows above and one to the right, like this case, then that term is 0. You don't have to calculate it. You go to the next row. You find everything in this array. And then once you complete everything, the next step is to look at the first column. As you can see, all numbers in the first column. By the way, the formulas for finding E1 and F1 over here. Next, we'll look at the first column. As you can see, if we start from the top, we see 1, 4, 2.5, 2, 3. They're all positive. Then we get to a negative number from 3 to negative 5. And then from negative 5 to 4, and again, another sign change. So we are seeing two sign changes if we go from the top to the bottom of the first row. That means the system is unstable and it will have two poles in the right half plane. That is the result of using the Ruth array in this example. We can check our answer using MATLAB. This is the alternate. This is not the continuation of the solution. If we could do this from the beginning, there was no point in using the Ruth array. To solve the characteristic polynomial, you can use the roots command in MATLAB. Just give the coefficients of your polynomial in an array to that command, and it will find the roots for you. If you look at the roots here, two of these roots are having positive real parts, 0.679. That means they're on the right half plane, and that confirms the answer we found from the Ruth array. The Ruth array does not give us the exact values, the values of the poles, or the location of the poles. It only tells us how many poles we are going to have in the right half plane. It said 2, and we checked with MATLAB. We see that there are 2 poles in the right half plane for this example. Here's the next example. So we have another characteristic equation given here. To check its stability, remember we first check the necessary condition. In this case, we see that one of the coefficients, this one here, is negative. So they're not all the same signs. That means the system does not have the necessary condition and it will be unstable. No need to set up the Ruth array if we want to see if the system is stable or not. From here, we know that it is unstable. So we see that because of that one negative coefficient, the system must be stable. Let's check our answer with MATLAB. Again, we will find the roots of the characteristic polynomial. Just give the coefficients of the characteristic to the roots command. It'll find the roots for you. Two of the roots, as you can see, have positive real parts. That means they are in the right half plane. So that means the system is unstable, and our answer is confirmed. Stability versus parameter range. In the two examples before, we had a characteristic polynomial which was completely known. In some example, we have a parameter in our system or in the controller, basically, that does not have a known value yet. We haven't picked a value for it. Like in this example, our controller is a proportional controller with a constant k as its transfer function. So we want to know for what values of k, or basically for what range of k, our system will be stable. This would be the first thing that we should do when we want to design that controller. First, find the range of k that keeps the system stable. How to do this? We will follow the same thing. The only difference is that in our root array, we are going to have terms that depend on k. No problem, we will set that up. We will just look at the first column at the end and determine the conditions by which all the terms in the first column of the root array will be positive. First step, we need to find the closed loop transfer function, look at its denominator, get the characteristic polynomial. So multiply the two blocks in the forward path. That would be our g. Feedback path is 1, so h is 1. Use the feedback loop equation g over 1 plus gh, and simply simplify that, get the characteristic equation. Characteristic equation is right here, the denominator of the transfer function. That doesn't look like the form we wanted, so what we should do is to expand everything in that characteristic polynomial and combine similar terms. Then we get to the next slide. Once we expand the denominator of the transfer function and combine the similar terms, for example, if we have a k times s and a minus 6 times s, make sure you combine those into one term. Order everything in the order of highest order of s to the lowest, and then we put the coefficients into the first two rows of the root array. We have the coefficients of 1, 5, k minus 6, and k. So we put the first one in the first row, then second row, back to first row, second row, and so forth. So we put these two in, we complete the first two rows. Then we have two more rows to find. First, we need to find b1 and b2. For example, b1, to find b1, we have negative of the determinant of the first column in the row in the two rows above, 1 and 5, and then the column to the right of the term we want in the two rows above, that's k minus 6 and k, divided by the first term in the row above, which is 5. So this is b1. For b2, we have negative of the determinant of the first column in the two rows above, 1 and 5, the column to the right of the term that we want in the two rows above, which is the column here. There is nothing there, so that means they are both zeros. The denominator is first term in the row above, which is 5. That determinant is 0, so b2 is 0. Similarly, we'll find c1 and c2. Now let me erase these, and we'll see the answers and take it from there. b1 and b2, then c1 and c2. Once we find all the values, we need to go back to the first column of the root array. Everything in the first column must have the same sign or must be positive for our system to be stable. Remember, we wanted to find the range for k that keeps the system stable. The first two terms in that column are the known and positive. So we need B1 and C1 to be positive. B1 is here, so that term being positive is one condition. C1 is here, and that being positive is our second condition. So these are the two conditions that need to be satisfied. Remember, both of these must be satisfied for the system to be stable. The first condition is equivalent to K being greater than 7.5. Second one says K has to be greater than 0. Since both have to be satisfied at the same time, this is equivalent to K being greater than 7.5. That is the range for K. If K is anything greater than 7.5, our system will be stable. Generating the step response of the transfer function in MATLAB for three different values of K. So let's pick three different values, K being 5, 7.5, and 10. And we are seeing the step response. That means the input is the step unit step function. Remember we said K being 7.5 or K being greater than 7.5 is the range for stability. The red curve is the step response for K being 10. You can see that it has some oscillations, but the oscillations decay and go away after some time. That corresponds to the stable response. The blue one, on the other hand, corresponds to K being 5. 5 is out of the stability range we found, so that creates an unstable response. You see the blue one keeps increasing. The amplitude increases and the response is unstable. The green one is when K is 7.5, exactly on the border between stability and instability. And as you can see, the response is a pure sinusoidal, and the amplitude does not increase and does not decrease. That's the marginal stability case. What if there are two parameters in our controller? So here's another type of controller. This is a proportional integral controller. We'll talk about this type of controller in more details later. But let's say that is the controller we have in that block. And here's our block diagram. What if we want to find out the range for two parameters, K and Ki, to keep the system stable? The first part is exactly the same as before. We have to find the closed loop transfer function, find its denominator, and the denominator would be our characteristic polynomial. So we'll find the closed loop transfer function, simplify that, look at the denominator. Denominator has already been simplified and put into the right order. So we have the coefficients in the denominator, 1, 3, 2 plus k, and ki. We need to put those into our root array, the first two rows, and then complete the next two rows. So here's our characteristic polynomial again. 1, 3, 2 plus k, and ki are placed in the first two rows. Then the terms in the next two rows have to be calculated. We have already calculated them and put the answers in place. For system to be stable, we need all terms in the first column to be positive. The first two are already positive. So we need to look at the other two. Two conditions are given. This term must be positive, which means its numerator must be positive. And this must be positive, which means Ki has to be positive. So two conditions. Here's how we get the conditions of stability. So we have one condition only in terms of Ki, which says Ki has to be greater than 0. The other one relates both K and Ki together for this problem. So that means Ki has to be anything greater than 0. Anything greater than 0 for Ki works. For K, we can rewrite that first equation as K has to be greater than Ki minus 6 divided by 3. That means we have two equations that have to be satisfied. For any given value of Ki, there is a specific minimum value for K depending on that Ki value. Another way to show this region is to draw the two lines that are obtained from these two inequalities. The first one, let's draw the line of ki equal to 0. Let's say this is ki on the horizontal axis and k is on the vertical axis. The ki being equal to 0 line is this line here. Draw the line. Now our inequality is ki has to be greater than 0. That means the right side of this line is acceptable. The other condition says k has to be greater than ki minus 6 over 3. Draw the line of k equals ki minus 6 over 3 gives us this line. K being greater than this means above this line is acceptable. So above this line and to the right of this vertical line are the acceptable region. That means this blue area is the allowable region for selecting k and ki. There are a couple of special cases that could happen when we are setting up the Ruth array. One is if a first term in a row is 0, but there exists at least one non-zero term in that row. If a first term in a row is 0, that creates a problem because when you want to calculate the terms in the next row, the first term the row above shows in the denominator of those formulas, and that creates a problem, a 0 being in the denominator. So we will have a problem finding the rows below that. To deal with these kind of issues, when there is a 0 in the first term of a row, but there are non-zero terms in that row, we will replace the first 0 term in that row by epsilon, which is supposed to be a very small but positive number. Pay attention to this. Very small positive number. Using that epsilon, we will complete the rest of the table, and then at the end we let epsilon approach 0 and find the signs of all the terms in the first column based on that, and get the conclusion out of that. If there is a sign change in the first column, the system is unstable. Here is an example. We have a characteristic polynomial here. 1, 3, 2, 6, 6, and 9 are the coefficients. We put those in the first two rows. Then we find the next row. When we want to find the term here in this third row in the table, the formula is negative of the determinant of the first column in the two rows above, and then the column to the right of the term you want in the two rows above, 2 and 6, divided by the first term in the row above, which is 3. If you find that determinant, it's 1 times 6 minus 2 times 3, so that's 0. We get a 0 for the first term in that row. That is a problem. Let's go ahead and find the next one. The next one in that row comes out to be 3. You should try to calculate that yourself. So it's non-zero. That means it is not a complete row of zeros. That would be a different case that we'll talk about it next. But what matters here is that we have a 0 in the first term of a row, but that row is not a complete row of zeros. We replace that row by epsilon, and then use that epsilon to complete the rest of the table. So for example, the term here would be negative of the determinant of the first column in the two rows above, 3 and epsilon, and then the column to the right of the term that we want in the two rows above, 6 and 3, divided by the first term in the row above, which is epsilon. This gives us 6 epsilon minus 9 over epsilon, which is what we have here in this place. We find the next term in that row, that comes out to be 9. We move forward to the next line. we find everything else in the table. As you can see, because we replace that 0 with epsilon, epsilon shows up in the rest of the table as a parameter. It's okay. You can leave it as epsilon. Once we complete the table, we will let epsilon approach 0, because we need epsilon to be a positive number, but very small positive number approaching 0. If epsilon approaches 0, first take a look at this term here. The numerator would be 6 times a very small number minus 9. That could give us a negative number divided by epsilon. We said epsilon is a small but positive, so a negative number divided by a positive number, this would be negative. The next term in the first column is right here. When we want to calculate this one, it might be better to multiply the top and the bottom by an epsilon, or yeah, that's probably the best way to do. So let's try multiply the top and the bottom by an epsilon. I'll get 3 times 6 epsilon minus 9 epsilon squared divided by 6 epsilon minus 9. Now if epsilon is 0 or approaches 0, then this term is 0 and this term is 0 and this is 0. So the answer will be 3 times negative 9 divided by negative 9, which is 3. 3 is positive. That's how we get the signs of these terms. So let me erase everything here. So the signs, this would be negative and this would be positive. Starting from the top to the bottom, we see there is one sign change here, from here to here, positive to negative, then another sign change from negative to positive. So 2 sign changes. That means obviously the system is unstable. There are 2 poles in the right half plane because there are 2 sign changes. If we use MATLAB to find the roots of that characteristic polynomial, these would be the roots. You can see there are 2 roots, S2 and S3, with positive real parts. They're both complex and they both have positive real parts, so they are on the right half plane. This confirms our answer. This is if we use MATLAB, for example, or a calculator to find the roots of our characteristic polynomial. The other special case is if we find a row that is completely 0. All terms in one row are 0. If that happens, that means there are roots of equal magnitude lying radially opposite in the S-plane. Whenever that happens, this is the case. Two of the common cases that could happen are if there are 2 poles on the real axis with the same distance to the origin, like this figure to the left, or 2 poles on the j omega axis with the same distance to the origin. These cases are both cases where there are poles with equal magnitude lying radially opposite in the S-plane. So they're basically symmetric with respect to the origin. These are not all of the poles, but some of the poles, only 2 of the poles of the entire characteristic polynomial. In such cases, what we're going to do is to form an auxiliary polynomial from the last non-zero row. So basically from the row above the row of zeros. And then take the derivative of that auxiliary polynomial with respect to s, and then use the coefficients of that derivative to fill in the place of the 0 row. And then we'll do the rest of the table. So let's see an example. Here is a polynomial, an example. We have the coefficients 1, 2, 1, 2. We'll put in the first 2 rows. The next row we will get 0 and 0. You can try to find those and to make sure they will be both zeros. We have a row of zeros. Before we do the rest of the table, we are going to have to, so we cannot really complete the rest of the table now because we have a 0 in the first term in that row. We're not going to replace it with an epsilon because this is a different special case. We have a complete row of zeros. We will get the auxiliary polynomial. The auxiliary polynomial is obtained from by using the coefficients in the row above. So what we're going to do is to multiply the first coefficient in the row above by the label of that row. So this is 2 times s squared plus the next coefficient in that row times the s to the power of 2 minus 2, which is 0. So you are going to have to skip one of the powers of s when you're writing your auxiliary polynomial. So 2 times s to the power of 2 plus 2 times s to the power of 0 is the auxiliary polynomial. Then we'll have to take its derivative with respect to s. That will be 2 times 2s, which is 4s, plus the derivative of 2 is 0. So this is the derivative. With the derivative, we have two coefficients, 4 and 0. We're going to replace those in the row of zeros. So as you can see, back to the table, that 0 is replaced by a 4. Then we will use that to complete the rest of the table. And now that the table is complete, we will look at the first column to find out if there are any sign changes. There are no sign changes in the first column. That means there is no pole in the right half plane. But because we got a row of zeros, we also know something extra about this system. That is, there are poles that are lying radially opposite to the origin. So the only case that this could happen, and still there are no poles in the right half plane, is if we have two poles on the j omega axis and radially opposite from each other. If we use MATLAB to solve and find the roots of this characteristic polynomial, these are the roots that we will find. If you take a look at S2 and S3, these two roots are positive j and negative j on the j omega axis. We still don't have any poles on the right half plane. If you remember from our discussion about the stability, if there are poles on the j omega axis that are not repeated, system is stable, and this is exactly that case. Another example, we have a characteristic polynomial like this. We'll put the coefficients of the first two coefficients into the first two rows, then find the next row, the row after that, and then when we get to this row, it looks like we will get two zeros. So we have a row of zeros. We cannot complete the next row before we do something about this row. So what we're going to have to do again, we have to go back to the row above this row of zeros, get the coefficients of that row, use that to set up the auxiliary polynomial. So row of zeros, go back to the row above, pick the coefficients 3 and 12, 3 times s squared plus 12 times s to the 0, or simply 12. That's our auxiliary polynomial. Take its derivative with respect to s. Derivative is 6s. There's only one coefficient, and that coefficient is 6. So we're going to use that coefficient and replace the first term in the row of zeros. So we replace that row by 6 and 0 instead of 0 and 0. Next, we will complete the rest of the table, which is just one row remaining. We'll find the value for that one remaining row using our formula, and now the table is complete. Look at all the terms in the first column. They are all positive. That means there is no sign change, nor roots in the right half plane. Because there was a row of zeros, we must have radially opposite roots because of the row of zeros. So again, this is like the previous example. No poles in the right half plane, but there are radially opposite poles. That means there should be at least two poles on the j omega axis. If we use MATLAB or a calculator to find the roots of the characteristic equation, we will find that two of those are at positive J2 and negative J2. By the way, the number of poles that are lying radially opposite would be equal to the degree of the auxiliary polynomial. So in this case, the auxiliary polynomial is of degree 2. That means there are two poles that are lying radially opposite from each other on the S-plane. And that is also confirmed. This is again an unstable system because there is no pole in the right half plane, and those that are on the j omega axis are not repeated ones. So again, the result is stable. Another example, this is a characteristic equation. If we want to just check a stability, what we are going to do is to first check the coefficients. They are not all the same sign, so we should directly know the necessary condition is not satisfied and the system is unstable. But if we want to do some practice, put the coefficients into the first two rows, then the third row comes out to be all zeros. You can do the calculations. So here we have to again use the auxiliary equation. Go back to the row above, use the coefficients in the row above. These coefficients are 2, 48, and negative 50. Remember, the first term in the auxiliary equation is 2 times the label in that row. That's s to the power of 4. 2 times s to the 4 plus 48 times s to the 2 minus 50 times s to the 0. So row of zeros, auxiliary polynomial, take its derivative, use the coefficient of this, which are 8 and 96, to replace the row of zeros. So replace that row, and now complete the rest of the rows. Now the table is complete. Look at the first column. We don't have all positives. There's one sign change from the top to the bottom. There is only one negative term at the end. So there's one sign change. That means there's one root in the right half plane. System is unstable. We knew this from the beginning because not all coefficients were positive. And also we have radially opposite roots. This time we should have 4 radially opposite poles because the auxiliary polynomial is of degree 4. There is only one of them in the right half plane, so the only case that could create this is if we have 2 radially opposite poles on the real axis and 2 on the j omega axis. Again, if we use MATLAB or a calculator to find the roots of that characteristic polynomial, we will find that these two are on the j omega axis, radially opposite, and these two are again radially opposite but on the real axis. One is at 1, the other one at negative 1. Confirms everything that we got from the root array. Also, S3 you can see is equal to positive 1, which means it has a positive real part. That is what makes the system an unstable system. This is the end of chapter 2. After watching this lecture video, you should be able to complete the first assignment on Blackboard.